Okay, in the previous slide, we studied the Coulomb's law between two charges. So in this case, for each charge, there was only one Coulomb force acting. And then now, let's think about the case when there are more than two charges. So therefore, for one charge, there are more than two forces acting. Then what do we have to do? Remember that a Coulomb force is just a force. And we already learned about the superposition principle in the spring semester. So therefore, when you have more than one forces, try to calculate each force one by one, and then finally try to make a summation. And in doing so, if the charges are not along a straight line, then try to use the rules of vector summation. Now let's try two examples. First, from the simpler example in which there are three charges located along a straight line, as shown in the figure. And now it is asking us to calculate the total force acting on Q1 by Q2 and Q3. So in this case, we have to perform the calculation twice, first between Q1 and Q2, and then between Q1 and Q3, and then make a summation. Now let's think about the Coulomb force between Q1 and Q2. Now the charge Q1 and Q2 are both positive charges, and then they are separated by the distance r. Then what is the Coulomb force? The Coulomb force between them must be K multiplied by Q squared divided by R squared. So it is because we already assumed that all the charges have the size Q, and some of them may be positive and some of them may be negative, but the magnitudes are all Q. So that's why we have Q multiplied by Q, which is equal to Q squared. And then how about the Coulomb force between Q1 and Q3? Now the Q1 and Q3 in this figure have opposite signs, but nevertheless their sizes are Q. And they are separated by the distance 3/4r. So therefore, now the Coulomb force between them must be K multiplied by Q squared divided by the square of 3/4r. Now you see that these two forces, F12 and F13, have a different size. And then we already probably have an idea that they will be pointing along different directions. So between Q1 and Q2, there will be a repulsive force. So therefore, from the viewpoint of Q1, it is pushed to the left-hand side. Okay, and then between Q1 and Q3, there must be an attractive force. So therefore, Q1 is being attracted to the right-hand side. So therefore, we realize that we have to make a subtraction between these two forces. And of course, in the vector form, we are still writing with the positive summation between the two, but remember that these two vectors are actually pointing away from each other. So therefore, what we eventually have to do is making a subtraction. But by convention, we always have the right-hand side to be the positive. So therefore, in this case, you have to use a negative sign for the force between 1 and 2, which is F12. So the total force will be a minus F12 plus F13. And then if you calculate by inserting these two values, then this is what you get. Now let's try another example, which is a little bit more difficult because now three charges are not located along a straight line, but they are forming a triangular shape. And in this case, we are again asked to calculate the total force acting on Q1 by Q2 and Q4. Now again, the Q1 and Q2 are located along the x-axis and separated by r. Even though it's not shown in this figure, let's assume that they are separated by r. Then the Coulomb force will again be simply K multiplied by Q squared divided by R squared, which is the same as before. And then the Q4 is located again at the distance 3/4 r from Q1. So therefore, the size of the Coulomb force between Q1 and Q4 is actually the same as the size of the Coulomb force between Q1 and Q3 in the first slide, in the previous slide, I mean. So therefore, the calculation up to this part is simple, but we have to consider the fact that the force are now not along a straight line with respect to each other, but they are at an angle. But we know that Q1 and Q2 are both positive, so therefore the Q1 will be pushed to the left-hand side because of the Q2. And then Q4 is negatively charged, so therefore force onto Q1 from Q4 will be pointing at an angle. And then let's call the angle theta, which is an angle between this vector and then the x direction. So in this case, in order to get the total summation of these forces, we have to think about the components along x first, and then along y, and then if necessary along z direction too. But in this case, we don't have to think about the z direction. Okay, so what is the force along x direction? Now F12 is along negative x direction, so it must be included. So therefore, force along x is the summation between minus F12 and plus F14, but multiplied by cosine theta. As you know, we have to multiply by this cosine theta in order to get the force components along the x direction. Okay, and then by inserting the numbers we already have calculated, this is the total force along the x direction. And how about the force along y direction? The force between Q1 and Q2 is strictly along x direction, so therefore there will be no force along y direction. So therefore we don't have to worry about F12, but we only have to include F14, which is between 1 and 4. And then in this case, instead of cosine theta, we have to multiply by sine theta, because this vector component is along the y direction, and it is the F14 multiplied by sine theta. Okay, and then again, this is the force along y direction. And finally, by using these so-called scalar components along x and y directions respectively, we finally get the total vector by multiplying force along x direction. And then this is, if you remember, the unit vector along x direction, simply making the vector point along x, and then y components multiplied by the unit vector along y direction. Okay, this is how we do the calculation summation of the forces. Okay, we are almost done with chapter 21, but before closing, let me summarize a few important things you have to remember about charges. The first is that the charges are quantized. This means that the amount of any charge must always be the elementary charge multiplied by some integer. So the integer can be 2 or 4, 5, 10, 1000, it can be anything, but it cannot be smaller than 1, or it cannot be some number like 1.2 or 1.8. It always has to be integer. We already learned what this elementary charge has to be in terms of the size. And so we can, using some mathematical expression, that we can write that Q is large N multiplied by E, and it can also be positive or negative. And throughout the semester, if we write these capital letters to represent some number, it will suggest that it is an integer. Okay, so basically what it means is that the E must always be a unit of any charge. And then the second is that the charges are conserved. What this means is that you cannot really create or destroy net charges. So in the first example of the chemical reaction, so sodium ion first came with a one positive charge, and the KCl did not have any charge. And after the reaction, the charge has moved from sodium ion to potassium, but nevertheless, throughout the reaction, there will always be one net positive charge. And in the second equation, it looks as if the charges has disappeared after the reaction, but this does not mean that you can destroy charges. What it actually means is that positive and negative charges can combine, just like we are adding positive and negative numbers, and as a result, for example, if you add 1 and minus 1, it can become 0. It's simply the case that on the left-hand side, the net charge was still 0. And on the right-hand side, again, the net charge is 0. So when you say the charges are conserved, what we really mean is that the net amount of charge, it must be conserved. That's what it means. And charges tend to move through matter when there is a Coulomb force. And this is called a conduction. And this is how the current flows, so that we can operate electric appliances, like any appliances like air conditioner or refrigerator or smartphone or anything. And when charges go through the matter, in some cases charges can flow very difficultly, and in some cases it can flow very easily. So depending on how well charges conduct, we classify materials into insulators, semiconductors, conductors, and even superconductors. So we are not going too much into detail here, but later we will have some chance to discuss them a little bit more. Okay, so this is the end of chapter 21, and in the next class we will introduce the concept of electric field. And electric field is a very important concept because it actually makes the discussion of Coulomb interaction much easier and much more convenient. Okay, finally, this is the summary of today's lecture. From this lecture, you have learned what electric charges are, where electric charges come from, and how to calculate forces between electric charges using Coulomb's law. And in the next online lecture, we will study these various things. I'm not going to read them here for you, so please read them by yourself. But remember that this is about the next online lecture. But you have to come to the classroom lecture this coming Thursday. So before coming to the classroom lecture this coming Thursday, please remember that you have to solve all the online quiz attached to this online lecture. So I would suggest that before you close the web page, make sure you solve all the online quiz and then finally close the web page. Okay, so thank you for watching the online lecture. And then I will see you this coming Thursday in the classroom. Thank you.